Now next, let us try to understand what is program control block. Program control block is a diagrammatic logical representation of a process and its memory layout in Linux or Unix operating systems. Program control block help us to understand how process virtual memory works. Now here, process virtual memory is nothing but it is the chunk of global virtual address space which is assigned to a process. That chunk of virtual address space which is assigned to your process is called process virtual memory. So program control block help us to understand how process virtual memory works during the course of execution of a process. So let us see how program control block looks like for a Linux process. So remember, the program control block is nothing but it is just a diagrammatic logical representation of a process, right? So program control block helps us to understand that how the process and its memory layout works when the process executes. So going forward, you can see that this is the program control block. And this program control block actually represents the process in execution. So you can see that your process has different parts. The bottommost part in the program control block is actually the code section. So it is a part of memory which belongs to process virtual address space, of course. So it is a part of memory which stores the process code in text format, right? Now the process during its execution cannot change its source code. Therefore, this part of the memory is constant during the course of execution of a process. Next to the code memory lies the data memory. This memory actually stores your program or process global and static variables. Now again, your process global and static variables do not change during the course of execution of a process, and therefore this part of the memory, that is this data memory, is also constant during the entire lifetime of a process. So if you declare any global variable or static variable in your C program, those variables gets stored in the data memory of your process. The next portion of the memory is the heap memory. This memory actually stores the dynamic memory which is assigned to a process. So you must have used malloc and calloc system calls. What does these system calls do? These calls allocates dynamic memory to your process. So that is the reason that heap memory can actually expand, that is, it can grow and shrink. So if you call more number of malloc calls in your program and allocate more memory, your heap portion of virtual address space will grow. And if your program frees the memory, then the heap portion of this virtual address space will shrink. Now the remaining portion of the virtual address space is actually the total system available memory. So it is the portion of virtual address space that is still available to your process to be allotted. The heap region expands or shrinks when the process malloc or free the memory. So this is the heap region. And the topmost part of your program control block is actually the stack memory. This memory is assigned for process execution. It cannot grow beyond a certain limit. So you can see that there is a line. So this line actually represents that the stack memory cannot grow beyond this limit. And what actually gets stored in the stack memory? In the stack memory, the program stores all its local variables of all the functions, right? So as your program executes, and if function A calls function B calls function C, and function C calls function D. So you can see that the function A, B, C, D are actually creating a stack, right? So these function calls get stored in the stack memory, and that is the reason that this memory is called stack memory, because the sequence of the function calls actually creates a stack. Now each of these functions also have local variables. So those local variables are also get stored in the stack memory. And you can see that this program control block actually explains the memory layout of a process in execution in Linux operating systems. Now I ask you one question. Suppose you execute your program, and suppose you write a recursive program, and suppose you enter into an infinite loop and you keep on calling the function for infinite number of times. So what will happen? So what will happen? This stack will grow infinite. It means you will exhaust your entire stack memory, and the moment you cross this line, then your program will be terminated by operating system. Then your program is set to have caused stack overflow. So stack overflow is a situation when your program consumes the entire stack memory such that the stack memory crosses this barrier. You can see this red line is a barrier. So when your program causes stack overflow, the operating system kills your program. So this is the reason that you should not write a recursive programs which enters into infinite loop. So now let us do one small exercise to illustrate that what different portions of your program control block actually contains what portions of your program. So on the right hand side you can see that I have written a small program, right? So this program has one global variable. So as I said that this global variable will go in the data memory, right? And the moment your main function executes, the variable I is a local variable to the main function. Therefore, all the local variable will go to the stack memory. Similarly, my underscore name is also a local variable, so it will also go to the stack memory. Now the next thing is J variable. Now J variable is a static variable, and as I said that all the static and global variable will go to the data memory, right? So next is K variable. Again, K is a local variable, so it will be assigned a memory in the stack memory of the program control block. Now in this line you are actually assigning 100 bytes of dynamic memory to your program. So this dynamic memory will be allocated to heap memory. So your heap memory will expand by 100 bytes. And now your main program is now calling a function foo, right? Now calling of the function always occupies some memory, and that memory goes to the stack memory. So you can see that different portions of your program is allotted a memory which belongs to different portions of the program control block. That is, it could be code memory, data memory, heap memory, or stack memory. Now I ask you one question. What is the virtual address space of this program? Simply, the virtual address space of this program comprises of the data memory, heap memory, and stack memory. By definition, virtual address space is the set of all addresses which your program can access, and your program can access all the addresses that resides in data memory. That is, your program can access static and global variables, of course, and your program can always access any memory that is dynamically assigned. Therefore, heap memory portion also comes under your virtual address space, and of course your program can always access the local variables of all the functions. So when your function executes, you actually access the local variables. So the stack memory also contributes towards your program virtual address space, right? So virtual address space of a program is nothing but it is the summation of data memory, heap memory, and stack memory.